All right. So a couple of things just to start. The worksheet, I'd like you to turn this in a week from today. This is just some practice chain rule problems I was able to grab off the internet. You'll just turn, I want these to be turned in physically, like in class, turn them in. And it'll be counted as a quiz grade. Now, the bad thing about this chain rule worksheet is that it doesn't have any trig functions on it. There's no sine, cosine, tangent. So I'm going to find some more problems. In next class, I'm going to give you another worksheet with more stuff that has trig in it, all right? Because the chain rule is going to never go away, all right? It's going to be there for the rest of the time. Well, so same with product rule, quotient rule. So I want to make sure that you're getting consistent practice with it, all right? In terms of the exam, the grades were really good. This was our exam 1 average was a little bit below an 80. Exam 2 average was 80. The standard deviation, which was how far apart the grades are spread out, the number dropped, which means that we're closer together as a group, which is good. We had 8 A's. The blue is the exam 1, the orange is exam 2. So we had one more A on exam 2 than we did on exam 1. Same number of B's. The number of C's went down. The number of D's went up. The number of F's went down. These are the grades. This is of the 21 students that I have grades for. This shows the orange is the exams are right here, and then pick up this worksheet as well. That's due a week from today. So the orange is exam 2 and the blue is exam 1. So for example, this student right here, they got an 81.7 on the second exam. They got a 73.1 on the first exam, which means the grade went up, right? So if the orange is above the blue, that student went up. If the orange is below the blue, then the student's grade went down, all right? That's just to kind of give you an idea of where you are. You should be able to look at that and know who you are. So give you some idea of where you stand in the class. I think students that, you know, I'm concerned about the students over here, of course. So if both of your grades are on the low end, then we need to probably sit down and talk, all right? Because the material's going to get harder now. And so if you've already been struggling, we need to start to talk about what changes need to be made, what adjustments can be made. Maybe you need to go back and, I don't know, we need to talk, right? Everyone's going to have a different scenario. Any questions on the grades or the exam itself?
Is the last one going to be cumulative?
The final exam is cumulative in the sense that it's going to cover the whole semester, but it's not every single topic from the semester. So I will give you a review, which will give you some indication of what to expect. Please come get your exam and pick up one of these worksheets. So I know a few of you got here a little late. This worksheet is due a week from today. Turn it in, paper and pencil. You're going to hand it in as a quiz grade, all right? If you need any help on this, get tutoring, come to my office hours. Do not do your work on here. I did not intend for this to be, squeeze all your answers in here. Do your work on separate paper, all right? They don't give you really enough room to do it nice and legible. Yes?
Are we taking a picture and turning it to Canvas?
Nope, you're going to physically turn it in. Yep. All right, anything else before we get started? Yes?
What was with the grade for 2.5 and 2.6?
What was with it?
Yeah, because I didn't turn it in, but I still got a 100 for it. It was the one that was doing
The 2.5 and 2.6?
I think it was just 2.5.
2.5? You didn't turn anything in and got 100? Really?
Yeah.
Hmm.
It was the one that was doing
I don't know, maybe I made a mistake. Yeah, I mean, if you submitted something, I gave you a grade, but if you didn't, you shouldn't have. I might have accidentally. Yeah. I'll go change it to a 0. No, I won't do anything with it. You're doing fine, Andy. I'm not worried about you. All right, we're kind of getting to that point where Look, I mean, I'm not here to babysit you, you know? Like, you need to do your homework in here. Having you submit it online in Canvas, submitting your, you know, all that stuff, taking pictures, that's really, I told you in the beginning, that's just to kind of make sure you understand the expectation is you're doing your homework. We're what, how many weeks in now? 7 weeks in. We're almost halfway through the semester. I mean, like, I shouldn't have to force you to show me you're doing your homework, right? And I think with the distribution of the grades, I'm happy with this. If our average was like a 68, I'd be checking your homework. I'd be making sure you're doing it. I'd be really on top of that, right? But this is good. I mean, it's a good average. So, all right. Just coming in? Yeah, thank you. All right, so today is a big day, all right? Today is a real big day because we're going to start talking about the next section, which is called implicit differentiation. Let me make this a little bigger. So we're in 2.5. Now look, we still have chain rule to do, but what I mean by that is you need to continue to practice chain rule, which is why I gave you the worksheet. You already have the idea of chain rule. Like, you have the formula, you have the operation, what you need to actually do to do chain rule. But 2.6, we're going to move into it today, all right? So we're going to get right into this. Implicit, yes?
For this worksheet, do you want us to do the raw derivatives?
Yeah, raw derivatives are fine. Yeah, don't worry about cleaning them up. All right, so implicit differentiation. I want to go back to, I'm going to present something, and I'm going to just ask you what you think here. If I put this on the board, what would you tell me? Derivative of x.
With respect to x.
With respect to x. Now, you're assuming that, right? Because I didn't tell you otherwise. So what's the answer to that? 1, right? This is 1. I mean, that's what we've learned, right? And we learned this a while ago, right? We learned that before we even learned the power rule, right? And I proved this to you. We did the limit, and we did it graphically, and I did the actual limit and showed that this is true. And then I showed you, you know, another notation for this would be to write d dx of x, and that would mean the same thing, and our answer would be 1, right? And I told you sometimes this notation's better, sometimes this is better. Well, now we're going to start to focus on this notation, because what this notation is telling us is what we're differentiating with respect to. So visually, this is the way I try and think of this. We have this function. Sorry, I still sound congested. I feel okay, but all right. So we have this function. I'm going to say f of x equals x, right? Man, that's a weird blue. There's our identity function, right? Diagonal line. And when we say, hey, take the derivative, or what's the derivative with respect to x of x, what we're saying is, if I change x, dx, look at it as a little change in x. If I change x a little bit, so imagine we go to some point here. I'm gonna call it x, right? And imagine that we have a point here. If I change x just a little bit, just nudge the x in this direction just a little bit and have a new x next to it. So this little change, the difference between those two positions, right, that little infinitesimal change is dx. That little nudge to the right is that distance by dx. The question is, how much does the y change? Okay, how much does the y change? So the y value here changed from here to here, right? That would be our dy. And then the derivative is the ratio of those two. It's the ratio. It's the change in y divided by the change in x, which in this case should be 1, because the identity function, if you move over, you go up by the same amount, right? So this hopefully all makes sense, like visually and notation-wise, this hopefully makes sense. This is how much x changes by, and then you want to know, well, then how much does x change by? Because it's the identity function. So you could look at this as being dx over dx like this. Like, just imagine sliding that x here. And then anything over itself should be 1, right? All right, how is that different than this? If I had put x squared up here and asked you for the derivative, we all say 2x. We're all happy with that, right? But the other notation is d dx of x squared. What's that equal to, right? So if I were to look at a graph, x squared is a parabola. And if I pick some point x, here's the point, and then I nudge to the right a little bit, right? Just move to the right just a little bit. That's now dx. Now I'm up here. The question is, again, how much does the y change by? Right? And I take that ratio. What's this change divided by this change? Well, it should be in this problem what? 2x. All right? It's not 1 anymore. The ratio is not constant like here. The ratio is twice the x value. So that, right? All right. With that said, I now want to look at a different problem. I'll do it over here. What if I write sine of x squared, and then I want the derivative? All right. What am I going to need to do that derivative? Chain rule, right? That is composition of two functions. That is the x squared function inside of, right, inside of the sine function. So the way that we did this in class is we said, okay, we start with the outer one, right? The outer one is sine. We take derivative of sine of this rag, and we get what? Cosine of the rag, right? Cosine of the rag. And then chain rule says you now multiply by what? The derivative of x, of the inside, derivative of x squared, which is 2x like we did over here. Yeah? Yes? Okay. What if I do this? And I'm gonna put a big star next to this one. All right. What if I say take the derivative of sine of x? And this time I'm going to write d dx. It's the same thing as me writing the prime, right? Same thing. Except now I'm being very explicit. I'm saying, look, we're nudging x a little bit and we want to know how much the y changes. So is this easy? What's the derivative of sine of x?
Cosine of x. Cosine
of x, right? I agree. But I want you to just kind of like refocus the way you're looking at this. I want you to look at it as composition. I want you to cover up that x. What's the derivative of sine of this rag? Cosine of the rag. Right? What was the rag? X. Okay, chain rule says times, right? Now, I need to take the derivative of what's inside, right? With respect to what? X. So I'm going to write that a little different. I'm going to write it derivative with respect to x of x, right? That's the chain rule, isn't it? I'm taking derivative of the outer function, sine. Derivative of the outer function is cosine of x. But then now I need to multiply times the derivative of what's inside, which is the derivative with respect to x of x itself, which is just what? This is just 1, isn't it? So our answer is what? Cosine x, which is what we said it should be to begin with, right? But do you see that you actually have the chain rule there? Like we've been doing the chain rule without actually knowing we're doing the chain rule. Because we've always had to eventually take the derivative of what's here, and if it's just x, the derivative is 1. Okay? I'm going to give you another one. What if we take the derivative with respect to x of x squared? I know the answer is 2x. You know the answer is 2x, right? But let's try it with this idea of chain rule. Do you see that we have a function being squared, right? The rag being squared. What's the derivative of the rag being squared? Oh, oops. What's the derivative of the rag being squared? 2 times the rag, right? 2 times the rag to the first power. I'm going to use my mouse instead, right? We have my mouse squared. What's the derivative of my mouse squared? 2 times the mouse to the first power. Oh, it's magnetic. All right. Yes? Now, what goes here? X, right? The mouse, okay? I'm not done. Chain rule. Times. Now, I've done the squared already, haven't I? Now, I need to take the derivative of the x. And the derivative of the x with respect to x is 1 again, right? And so since this is 1, we just get 2x. I know you're sitting there going, why are you making this more complicated than it has to be, right? Like, why are you complicating this? Right? Here's why. What if I ask you for this? What's the derivative with respect to t, all right, of sine x? Okay, now this is different, all right? See, this is different? We're differentiating with respect to t, which means we're going to nudge t a little bit, and we want to know how much x changes by. Or sine x changes by. But there's no t's over here, right? Over here, look, derivative of sine x is cosine x, and we're done. So let me say this again. If I want to know how much sine x changes, right? If I nudge x a little bit, right? If I nudge x a little bit, how much will sine x change by? It will be equal to cosine x times the change in x with respect to x, which is 1, right? That's the rule, the chain rule. Over here, when I take this derivative, I start by, again, let me get my mouse again. Using chain rule, what's the derivative of sine of my mouse? Cosine of my mouse. Now what's my mouse? X, okay. Chain rule, times. Now I need to take derivative of x, right? With respect to what though? T. So I write d over dt of x, like that. Is this 1? No, because these variables aren't the same. Now, what is it? I actually don't know what it is. But what I can tell you is this. I can move this x up here and just write it like this. So let me try and explain what this is saying. If I want to know how much sine x changes, if I nudge t a little bit, then it will be cosine x times the change in x with respect to t. So however much x changes if I nudge t. I have no idea what that's going to be, but this is the actual chain rule applied on this function. All right, let's do another one. Yes?
Does d just mean an infinitesimal amount of change?
The dt is an infinitesimal amount of change of the variable t. And then dx is how much the x changes when you actually change the t. And this division is the ratio of the two. Okay? What we're not seeing yet in this example is how the t and the x are connected. I haven't given you any connection between x and t at this point. The main idea here is that everything we've been doing, this prime mark has always implied that we're differentiating with respect to x. But now we're about to move into problems where we need to actually be explicit in terms of what we're differentiating with respect to. What's the thing we're nudging? Are we nudging x? Are we nudging t? Are we nudging some other variable? And how does that affect everything else? Excuse me. Go ahead.
So I guess what I'm confused about is like the exact definition of d. It's like I know how to work with it, but I don't know like exactly what that means.
Okay. Let's just go back to an easier example. If I give you y is some function of x, right? Yes? And then I pick some point here, x, and some other point here, x plus h, and draw a secant line between the two. Then the tangent line is what happens when you move this over to here, right? And so we take this limit, h goes to 0, f of x plus h minus f of x over h. That's the definition of the derivative of that function at x, right? Okay, now when you let h go to 0, what's happening is this point's moving along here, right? So right now, if I don't move the point, if I don't move that point, I have a little triangle here, don't I? I'm going to blow that triangle up. This right here is my change in x. That's how much my x changes by. And this distance from here to here, that's my change in y. Right? Slope is rise over run, which is change in x over change in y. Sorry, change in y over change in x, right? That all okay? We have two distinct points. We have this notation. If we take the limit and we let h go to 0, what happens is that this triangle becomes smaller and smaller and smaller, right? So this triangle now shrinks and becomes this infinitesimally tiny little right triangle, right? And it's actually going to become a point eventually, right? But as I take the limit, it gets infinitesimally small. As it gets infinitesimally small, we stop using this notation and this notation, and we put dy here and dx here. So that implies the limit is being applied. Does that make sense? And those are getting infinitesimally small. So dx for us here represents, like when I say it's the nudging, it's actually me trying to make this little tiny triangle appear. Does that help or no?
Yeah.
Okay. Good question, because delta x and delta y are not the same as dx and dy. Delta x and delta y is if you have two distinct points just sitting there static. And if you start to move the points closer to one another in a limit, then you change it to dx and dy. Okay, let's do this one. I'm going to do this one right here, the x squared, derivative x squared. Or let's do something different. Let's do this one. What's the derivative with respect to x of y squared? Notice that the thing you're taking the derivative of, y squared, the variable is y, right? But you're differentiating with respect to x, right? And so these two variables are different, which means that we're not going to get a 1 to ever pop out when we do the chain rule. It's never going to be dx over dx, right? So we start again, chain rule, right? We have something squared, my fist, right? My fist squared. What's the derivative of my fist squared? Two of my fists, right, to the first power, right? And then we say times, now be careful, that's a 1, not a prime, okay? Times, now the chain rule, we've done the squared, now take the derivative of y with respect to x, which should be what? dy over dx, not 1. And that's it, that's your answer. You'll see why, you'll see in a second how this is all going to come together. And next week when we start doing the dreaded word problems, okay? I've told you about these or no? Related rates is what we're going to do next week. Related rates are word problems. And if you ask any Cal 2 student what they hated about Cal 1, they're going to say related rates. Unless they've completely blocked it out of their minds. They may have forgotten it because they blocked it out because they hated it so much. Yes?
Okay, that's like how much a balloon is like.
Yeah, a balloon is being inflated at, blah, blah, blah. Yeah, those problems. They're fun, yes? Okay, it depends on how hard they get. I mean, like, some of them can be pretty basic, other ones are going to be hard. All right, make sense? Any questions? How about this one? D dt. So I want to know the rate of change of something with respect to t, and here's what I want you to tell me. X squared plus y cubed. Ooh, okay. I've got two variables in here, x and y, right? But this variable t is different. Now, I want the derivative of this. Do you see that there's a plus sign between these? So remember, with derivatives, we can separate into two. So we can still do that, all right? So this is going to become the derivative with respect to t of x squared. I've got to figure out what that is, plus the derivative with respect to t of y cubed.
So multiplication though.
If it was multiplication, we'd have to do the product rule. Exactly. We'll do one of those. So what's this derivative going to be? 2x times, what? Yeah, dx over dt. Does everybody see that? Do I need to show or talk about this in more depth? Right? Because this variable and this variable are not the same, you have to do chain rule. Derivative of something squared, 2 times that something, right? Times derivative of what's here with respect to t dx dt. Not 1. Plus, all right, now this one. What do you think? What's the derivative of y cubed with respect to t? 3y squared, so you're just using the power rule on that first, right? 3y squared, but because of chain rule,
Times 2dy over dt.
times, we already did the cubed. You don't need to worry about the cube. That's, we already took care of the cubed, right?
Yeah, now you're taking the derivative of the inner, which is, oh, just y? Oh.
Just y, right? So dy over dt. That make sense, everyone?
Well, if you're dropping the 3, oh, okay. Okay.
My fist
Yes.
cubed, right? You take care of the 3 first, got that, and then times the derivative inside.
Got it.
Any other questions? How would that problem change if I did this instead? d dx x squared plus y cubed. So could I still split it into 2?
It's gonna be 1.
Yeah, okay, so this will be d dx of x squared plus d dx of y cubed. Now on this first one, notice that your variable here, right? Your variable here, x and x, they're the same, right? So that means that somewhere in the chain rule, I'm going to get a 1. Because I'm going to get a dx over dx eventually, right? Where here I have a y and an x, so I know when I do chain rule, I'm going to get a dy dx somewhere, right? But I got to get through the chain rule first. So derivative of this would be 2x, right? That's the power rule, times now the derivative of what's here, which is 1. Now I'm going to write dx over dx just to make sure everyone understands I'm doing the chain rule here. Dx dx, right? Plus, now this one, 3y squared, that's my power rule, but then continue with the chain dy dx, right? Questions? Come on, this is your chance to ask questions. This is just 2x plus 3y squared dy dx. We good? Let's go ahead and do that one that, what if this was a product? Let's do this. Let's change that to a product. I'll write it up here. We want the derivative with respect to t of x squared times y cubed. All right, so I look at that, I say, okay, I'm differentiating with respect to t, and then I've got x's and y's here. So I know that I'm going to have, somewhere in here I'm going to have a dx dt, right? Somewhere in here I'm going to have dx dt, and somewhere in here I'm going to have dy dt, right? Both of those things should appear. Nowhere should I ever get a dx dx. But to take this derivative, it's not addition, right? So I can't split it into 2. What I can do, though, is apply the product rule, because there is a product there, right? So according to the product rule, this should be the derivative of the first one times the second plus the derivative of the second one times the first one, right? So I'm going to write that down. I'm going to take the derivative with respect to t of the first one times the second one plus the derivative with respect to t of the second one times the first one. Do you all agree that that's the product rule written out? And now, at this point, I have to do these, right? So this one, we just did that a second ago, right? This right here is 2x dx dt. And then I still have times y cubed. And then plus this one is 3y squared times dy dt times x squared. Make sense? We're done. Let's do this one, change that to a product, and see how things change. You'll see why we're doing this in a second. I just wanted to get all the mechanics of it down first. You'll see where we're going in a minute. So what is the derivative with respect to x of x squared y cubed? I still have to do product rule, right? Do I have to do product rule? So this is the derivative of the first one times the second one plus the derivative with respect to x of the second one times the first one. Product rule. What's this? 2x and then times dx dx, right? Which is going to be a 1. So is it all right now if I just put that as 2x without actually putting the 1 next to it? And then times y cubed. I'll just put y cubed. It's implied that that's multiplication. Plus, now this one is not going to give me a 1, right? We're going to have a dy dx pop out of this. So this will be 3y squared times now the dy dx, and then times the x squared. That's it. So you'll see the difference between these two? They both required product rule. The only difference was here, right, the dx dt and the dy dt, right? We had both of them. Here, the dx dx became a 1, and then the dy dx did not become a 1. All right? Okay, why are we doing? Oh, I want to do one more. Sorry, I want to do one more. How about this one? I'll make this one kind of ugly, all right? What if I wanted d dx of sine of x to the 4th y minus y to the 3rd? Oh, forgot a parenthesis. You ready? I'm going to start cranking up the thinking here now. What do you see? Chain rule, right? You see sine and then inside of it a bunch of stuff, right? And you have a product rule in there, right? Oh man, what a mess.